of this sum is just a times f prime plus b times g prime. And so we say that we can differentiate term by term. This means the derivative of a sum is the sum of the separate derivatives, derivative of the difference. Same thing. Now we're going to have an analog of that rule for antidifferentiation. When we integrate, that's the verb, when we integrate a sum, we can integrate term by term. And if there's a scalar, we don't ignore it, but we can pull it out front. So if I'm integrating this sum, I'll end up with a times the antiderivative of f, whatever that is, plus b times the antiderivative of g, whatever that is. That's term by term integration. Works the same way for subtraction. So there is an analog, differentiation and antidifferentiation, term by term. And maybe we could make an analog with the power rule. Let's go there. But that's going to be where there are no more analogs. So I stuck up in here in green our old power rule. We know how to differentiate powers of x. We know to bring down the exponent, leave the base, subtract from the exponent. And so as we went through 5 or 4.8, we just went backwards. We convinced ourselves that the antiderivative of x to the n would still be a power of x. We go up 1 in the exponent and divide by the new exponent. And we know our answer is a family of functions. Other two big rules from chapter 3. There is nothing like it with antiderivatives. You just got to know this. Yes, we have a product rule for differentiation. But we remember that the derivative of a product ends up being a big fat sum. So it's complicated. And the derivative of a quotient ends up being a difference. We have a product rule and a quotient rule for derivatives, but there is no product rule nor a quotient rule for antiderivatives. So if we run into quotients or products, we either have to rewrite them or we have to recognize, that they are the result of chain rule. Here's where we're going to hope today. If we spy a product in the integrand that's the result of chain rule, we're going to be able to use a technique called U substitution. So let me prepare your eyeballs to see a pattern. Okay, right here. This was our generalized power rule. So it's not just x to the n, but if we had some function to the nth power, like sine cubed, or arctan to the fourth, some function to the nth power. We're differentiating with respect to x. Remember, we would do the power rule, bring down the n, leave the base, subtract 1. But by the chain rule, we had to multiply by the derivative of the base. Preparing your eyeballs. This kind of product, which is the result of the chain rule, we have hope where we can integrate. So what will you be looking for? We're wanting to look for an inner function, which we'll call u, and its derivative as another factor. The next 6, 7 examples, I don't think you need to write them down. Okay, this is the old stuff, but we're training our eyeballs. Think way back. Maybe we had that quadratic cube. How did we apply the chain? Can you think through?
The outside, the derivative of the inside.
Got it. So the derivative of the outside, power rule, but don't forget the derivative of the inside. Linear function. What What if we had the square root of that quadratic?
Quadratic to the 1/2 and do something.
Right. Derivative of the outside, but don't forget the derivative of the inside. And we end up with that product. And we're focusing on u in a moment. U is quadratic, u prime linear. And all that other stuff from. Oh wait, just a rewrite. How do we rewrite that quotient?
To the negative 2.
And then it's just a power rule. Bring down the -2 and subtract 1 from 2. There's something missing. Can we spot the inner function? And is there a factor of u prime out to the side? Yeah. We're going to be able to integrate this in a moment and get back to where we started. Maybe a final exam question.
Cosine of y squared times 10x.
Times 10x. And then politely we pull the 10 and the x out front. What's the innermost function? I'm kind of stuck on quadratics, yeah, 5x squared. And its derivative is sitting out to the side as a factor. Okay, that's not going to videotape well. E to the x squared, is it?
X squared times e to the x squared?
So the derivative is almost itself. But we need the derivative of the exponent chain rule. This is e to the u, where u is x squared. E to the u and u prime. Familiar? We're still differentiating. There it is. Power rule and then chain rule. Memory fact and then chain. Never ends. Had a really good time with me.
Natural 1 plus 4x times squared.
Yeah. So we have this argument, 4x, and its arctangent, plus that argument squared times the derivative of the argument. Everything we're seeing as an answer ends up being a product. Those are our candidates. Those are where we have hope for taking the antiderivative. Now, these typically are the variables that the book uses. So if it looks like some funny word, just don't, it's not. Okay? So we've been looking at little functions f of x that were compositions. So there was an outer function, maybe capital F, and an inner function. That's going to be called u. That's our notation. And we know how the chain rule goes. To take the derivative of a composition function, we took the derivative of the outside, left the inside alone, and multiplied by the derivative of the inside. This is on videotape, but anyway. And this product right here can be written in Leibniz notation. Remember how that went? The derivative of f with respect to u. What's the derivative of u with respect to x? So now, going backwards. I don't know if you want to take notes. You might just want to process this with me. Now we're anti-differentiating. Going backwards. Here's my integrand. It's a product. We absolutely can't split up the integral and make it into 2. It won't work. You won't get the right answer. Instead, we have to ask ourselves, hey, is that the result of a chain rule? And I kind of look for an inner function. Okay, it's quadratic. And is there the derivative of the inner function? Yeah. So this is set up. So we're trying to recognize an inner function u, looking for u prime, hoping, and these are the conic. Now in practice, what you do, and I'll have to erase it, in practice you go off to the side and you tell the reader, okay, what's u? I'm going to make it this, 4x squared minus x. You define a dummy variable. Then think about Leibniz notation. If you differentiate u with respect to x, what do you get? 8x minus 1. And this can illustrate how we will then change bookends. This second line, this really isn't division, it's just Leibniz notation, right? It's really not division. But it helps the reader remember that we need a relationship among the differentials. Currently I have a differential, a bookend, called dx. If I'm going to change over to u, I'm going to have to change over to du. So I do a little scratch work, Leibniz notation, bring the dx over. And it says anywhere I have 8x minus 1 times dx, I can replace it all with du. Anywhere I have 8x minus 1 dx, I can wrap it up in a new differential. This is where it becomes nice. I'm going to replace this whole thing with du, and I'm going to rewrite this factor as 3u squared. And I make the u substitution. When we recognize an integrand is a product, a result of chain rule, we can make a convenient change of variance. No, it's just the old power rule. Can you integrate it? Not the 3. Go up to something cubed. Divide by the new coefficient. Oh. We learn as we go along. U cubed plus c. Because its derivative would be 3u squared. And then the last step, whatever u was, this is quadratic, we plug it back in. Maybe Jeffrey can see that, but nobody else can see it. So you'll see me record over here what I would generally write on the board. This is my scratch work. Integrand, it's a product. Is it possibly a u times a u prime? Yeah, it looks like 1 plus 5x can be u. So I can differentiate the left-hand side, abbreviate that with du. Differentiate the right-hand side, I get a 5, but I need a differential dx. Where does the dx come from? From the Leibniz notation. So the linear function becomes u, the 5 dx becomes du, and you just rewrite it. U du. Its antiderivative is going to be squared and divide by the 2. Maybe I can do this. I've got that right away. Maybe that'll be better.
Where do you get the half?
Yeah.
Oh, okay. So this is u to the first. I go up to a power and divide by the new power. Right. It's the count of up to a new power divided by the new power. Product. Is there hope? Yeah. So we call this u to the 1/2. And is this du? 2x. We're lucky we've got the 2. So we don't just substitute the 2x. We want to think of this product as the new du. What's the scratch work I expect? It's up here. When you look at it and you find the inner function, write it down as u. Differentiate both sides. Don't forget your differential. And anywhere there's a 2x dx, we can wrap it up into